Hey guys, it's Miss Gray, and this is AP Chemistry. Welcome to podcast 5.4, where today we're going to apply the gas laws to stoichiometric problems, and we'll also look at Dalton's law and how that influences the way we work with vapor pressure. Many of our gases are collected over water, so we have to deal with vapor pressure. All right, let's look at gases in stoichiometry. First of all, we know that reactions happen in moles, and a balanced equation describes mole-to-mole ratios of one reactant to another. We also know that at standard temperature and pressure, 1 mole of a gas occupies 22.42 liters. The trouble is, though, most of the reactions we do don't happen at standard temperature or at standard pressure. So we're going to have to use the ideal gas law to calculate the moles of a reactant or volume of a product or whatever it is we need to find out so that we can adjust for conditions other than standard temperature or standard pressure. Let me show you what I mean. In this example, we're going to look at the reaction of the calx of mercury, as it was once known. So when mercuric oxide is heated, it decomposes into its elements mercury, the liquid metal, and oxygen gas. So here's our question. What volume of oxygen gas can be produced from 4.10 grams of mercuric oxide at STP, or at a more reasonable temperature, if we're heating it up, it might be at, say, 400 degrees Celsius. Or then here's a pressure that's pretty common in Falcon, Colorado, 740 torr, which is less than standard pressure. So let's take these one thing at a time. We'll start with part A. At STP, what could we predict the volume of oxygen gas to be? So first of all, let's change grams to moles. That's our typical first starting place, right? When in doubt, we're going to go to moles. So we'll start with 4.10 grams of mercuric oxide. And what's our molar mass of that stuff? Mercury is 200 grams per mole. And then oxygen is 16 grams per mole. So that puts us right at 216.6 grams per mole. And of course this is mercuric oxide, and that's not exactly the stuff that I'm interested in, right? I want to know about the volume of oxygen. So I'm going to have to use the mole ratio to turn mercuric oxide into oxygen. So I'm going to have to come up here and balance this equation. I need 2 of these, so I can get 2 oxygens on this side. That means I'm going to get 2 atoms of mercury for every 1 molecule of oxygen that comes out. So now, mole-to-mole ratio for every 2 mercury oxides, 2 moles of mercuric oxide, I have 1 mole of oxygen gas. And that gives me moles of oxygen. I think that's the end of my T table. 0.946445506 moles. And of course I don't need all of those sig figs, but I'm going to keep them in my calculator because I'm not going to round until the end. I might perpetuate a rounding error if I did that. So we'll just keep them all in the calculator, but I'm not going to write that many sig figs anymore. Where are we at now? I have moles of oxygen, so I'm ready to use pivot now. I'm trying to find volume, so let's solve both sides for volume divided by P. So the volume is going to be my moles of oxygen times the gas law constant, 0.08206, and that is liters times atmospheres over moles times kelvins. And then my temperature is in kelvins. At standard temperature, it would be 0 Celsius, right? So we'll put 273.15 kelvins. And then my standard pressure is 1 atmosphere. All right, moles cancels, and atmospheres cancels, and kelvins cancels, and I am left with liters, which works out well since I'm trying to find the volume. Now, so that gives me a volume of 0.21 liters. I need one more sig fig, don't I? 212 liters. Sounds good. So for part A, at standard temperature and pressure, the volume of oxygen gas is 0.212 liters. All right, the trouble is we're not going to get mercuric oxide to decompose at 0 degrees Celsius. We're going to have to heat that sucker up. See this? Heat. Gotta add heat. So now what do we do? Well, now for part B, our temperature is 400 degrees Celsius. So add 273 to 400 and we get 673. Same number of moles still, right? So the volume is still the number of moles. What was that, 9.9 something? Let me look. 0.095, we'll say, times R, 0.08206, and that's liters times atmospheres over moles times Kelvin. And then my Kelvin temperature, 673.15 kelvins. And now divide by our pressure, which we would still assume is 1 atmosphere, because all we did here was change the temperature, right? So now, what do we get? 0.523 liters compared to 0.212 liters. It's almost doubled, right? More than doubled. Yeah. So now we have more space. We could have predicted that, right? When we increase the temperature, we have to increase the volume for oxygen. So now let's deal with a change in pressure. Let's solve part C. Suppose that rather than being at STP, our pressure drops to only 740 torr. I'm going to go ahead and change that pressure to atmospheres. I'd rather work in atmospheres than have to memorize the R value that uses torrs for units. So let's change 1 atmosphere to torrs. So 760 torrs is 1 atmosphere. 0.9737-ish atmospheres. And naturally I'm going to keep all those sig figs, right? I'm just going to keep them in my calculator and not bother writing them all down. So the number of moles is still 0.009, whatever we had, 5 something moles, multiplied by R, 0.08206. And then our temperature at standard temperature, we would be back to 273.15 kelvins. And now this time our pressure is non-standard. It dropped to 0.9737 atmospheres. Alright, now let's do this fun math. That is equal to 0.217876 and a whole bunch more sig figs. I only need 3 of these, so 0.218 liters. So it's almost the same as when we were under standard conditions, because the pressure didn't really change all that much and the temperature was still the same. So we didn't have a significant volume change, but it was certainly measurable. So here's a reaction with sodium bicarbonate and hydrochloric acid. This is a reaction that happens in your duodenum. As soon as the food leaves your stomach, then some sodium bicarbonate has to mix with it to neutralize the stomach acid before it goes through all of your small intestines for all the nutrients to be digested. So we've got to neutralize that very strong stomach acid. So this one says calculate the mass of sodium hydrogen carbonate necessary to produce 2.87 liters of carbon dioxide at 25 degrees Celsius and 2 atmospheres. Alright, so this again is not happening at STP. 2 atmospheres is twice the standard pressure, and 25 degrees Celsius is hotter than 0 degrees Celsius. Alright, so let's work this through. Calculate the mass of sodium hydrogen carbonate. So to get to mass, I'm going to need moles, right? And here's what we know. We've got this many liters, this much pressure, and this much temperature. So I'm going to use Pivnert. And this time I'm solving for the number of moles so that I can get to the mass. So N is equal to PV over RT. And my pressure is 2 atmospheres. My volume is 2.87 liters. R is going to be our 0.08206. And then temperature is in kelvins, 298 kelvins. Alright, so let's make sure that our units are going to work. We have liters times atmospheres over moles times Kelvin. So kelvins is going to cancel, and atmospheres cancels and liters cancels, and I'm left with 1 over moles, which means moles, right? This gets to kick back up to the top. Now that I've scribbled all over my writing, I'm going to try and do math with these numbers that I scribbled on. 2.87 times 2, and then I'm going to divide by the gas law constant, and I'm also dividing by 298 kelvins. So what do I end up with here? 0.2347 something moles of what? Carbon dioxide, it looks like, because that's the gas produced in the reaction, right? So now how do I change moles of carbon dioxide into grams of sodium hydrogen carbonate, also known as sodium bicarbonate? So we're going to have to use a t-table and do some stoichiometry. Take your moles of carbon dioxide and let's apply the mole ratio from our balanced equation. Ooh, I didn't even look to see if this equation was balanced or not. Nope, it doesn't look like it is. So let's see, I have 2 hydrogens. Oh yeah, sure it is, because I have 1 hydrogen here and 1 hydrogen here. We're good to go. So this is easy. For every 1 mole of carbon dioxide, I only need 1 mole of that sodium bicarbonate. Go ahead and put that step in there though, so that anyone reading through your work would know you did indeed apply the mole ratio from the balanced equation. Now let's change moles of the sodium bicarbonate into grams. So 1 mole of sodium hydrogen carbonate is its formal name, 84.01 grams per mole. Is that what you guys got for this one? I hope so. Of course you'll let me know if I made a mathematical error, right? You always do. Gives us 19.72 grams of sodium bicarbonate. And our question is, how many sig figs do we get to keep? Looks like our temperature is limited to 2 sig figs, so we're going to call this 20 grams of sodium bicarbonate. So now it says, if 27 liters of gas are produced at 26 degrees Celsius and 745 torr, when 2.6 liters of HCl are added, what is the concentration of HCl? All right, well, you know what we need for concentration, right? Concentration has units of molarity, which is moles per liter. So we're going to need to know how many moles of HCl and how many liters of HCl. And I'm not going to spend our time on this problem. I'm going to leave some of these for us to work out in class because we're just running out of time. Again, we have an example of stoichiometry and applying the ideal gas law. You know what? We're going to save this one for class time. And this one too. Let's look at Dalton's law. Dalton's law says that the total pressure in a container is the sum of the pressure that each gas would exert if it were alone in the container. So the total pressure, simple, is the sum of each of the partial pressures. So by partial pressure, what we mean is the pressure that's exerted by any particular component in a mixture of gases. Here it is mathematically, but think about like the Earth's atmosphere, right? The Earth's atmosphere is 80%, approximately 80% nitrogen gas, and then approximately 18% oxygen gas, and then some 2% of other gases. So what we mean here is that 80% of the pressure in the Earth's atmosphere is coming from the pressure that nitrogen gas brings to the table, and 18% of the pressure of our atmosphere is from oxygen gas, and only 2% is from other gases like water vapor and carbon dioxide and argon gas and whatever else might be flying around in the atmosphere. So for each gas, we would calculate its pressure using Pivnert, because of course we won't always be at standard temperature and pressure. But when it really comes in handy is when we need to describe all of the components of the same container. So in the same container, then the gas constant and the temperature and the volume are all the same because they're in the same container, right? So we could calculate the total pressure if we just add up all the moles. And then, of course, multiply the total number of moles by RT over V. That's it. So if you want to know what's the total pressure, you need to know how many moles are there. So Dalton's law is, of course, directly related to Avogadro's law that we talked about before. Here's one of the most important applications of Dalton's law when a gas is collected over water vapor. Remember this experiment from last year? Last year we used magnesium metal instead of zinc, and we placed it in a tube with hydrochloric acid, and the gas produced in this reaction bubbled across into a container that we had completely filled all the way with water. And as the gas bubbled in, it forced the water to displace out of the container and into our tub. That way, this bubble here is only from the gas that's produced in the reaction, but it's also going to have a little bit of water vapor. Since we're collecting this gas over water, then some of the water particles are going to be in this container too. They've achieved enough energy to bump out into the vapor phase. Especially if there's other gases bubbling through there, then those collisions of other gas bubbles with the particles of water might just give them enough energy to turn from a liquid to a gas. So we collect gas over water since it's a handy way for us to measure the size of that bubble, but then we have to deal with the water vapor. Of course, water vapor is not always going to be the same. It's highly dependent on the temperature. So the temperature at which the water exists determines how much pressure is coming from the water vapor. So let's look at an example of collecting a gas over water. It says when silicon dioxide, which is glass, reacts with carbon by heating, then we have this reaction. Silicon dioxide plus carbon makes silicon carbide plus carbon monoxide gas. What will be the volume of carbon monoxide collected over water that will be produced at 22 degrees Celsius and 657 millimeters of mercury when 96.25 grams of silicon dioxide completely reacts? So now first, do we have a balanced equation? Yeah, it looks like we're good there. We do have a balanced equation. So now we got to figure out how much of the pressure that we're measuring here is pressure from water and how much is pressure from the carbon monoxide gas. Oh gosh, we got all these problems. Look, this pressure is in pascals, this pressure is in millimeters of mercury, and the pressure that I like to work with is atmospheres. So we got a problem. Let's see, what's our vapor pressure of water at 22 degrees Celsius? I want to know that first before I get this table out of my way. 2,633.7 pascals, not kilopascals. So we're going for the volume of carbon monoxide. That's our target. And we have a temperature of 22 degrees Celsius. So let's add 273 to that, and we get 295.15 kelvins. And then we have a pressure that is called 657 millimeters of mercury. And we're not going to keep that. 760 millimeters of mercury is equal to 1 atmosphere, so let's change millimeters of mercury into atmospheres. What do we get? 0.8644736842 atmospheres. And what else? So I'm going to put here, let's see, we have this pressure is our atmospheric pressure, and that means that our water pressure plus our carbon dioxide pressure is going to balance out atmospheric pressure. I need to find the pressure of the carbon monoxide. So let's work that through. My water pressure is in pascals. So I had 2,633.7 pascals, and let's change this to kilopascals. Move this over 3 times. So 2.63337 or whatever that is, kPAs. Wow, can't talk tonight. And change kPAs to atmospheres. 101.3 kPAs is equal to 1 atmosphere. So my water pressure was 0.025999 atmospheres, and of course I have more numbers in my calculator, but that means the pressure of carbon monoxide gas is atmospheric pressure minus the pressure from the water vapor. So I'm going to do that math real quick. That gives me carbon monoxide pressure of 0.838-ish atmospheres. And I'm going for the volume. But first I need to know the number of moles. So the number of moles of carbon monoxide are going to be represented by, first of all, 96.25 grams of silicon dioxide. Now I need to know the molar mass so I can change grams to moles. For silicon dioxide, 1 mole is equal to 60.09 grams. And now I'm going to change moles of silicon dioxide into moles of carbon monoxide. So look to my balanced equation. 1 mole of SiO2 gives me 2 moles of carbon monoxide. So moles of CO, 3.2 moles of carbon monoxide. I'm running out of space here. Where am I going to stick my Pivnert? PV equals nRT. I'm trying to get my volume, right? The volume of carbon monoxide gas. So I'm going to take my moles, 3.2 moles of carbon monoxide, multiply by R, 0.08206, and my temperature in kelvins is 295.15, divide by my pressure, and this time I only want the pressure of the carbon monoxide gas, not the pressure of everything. So where was that number? This one, right? So still have that one in my calculator, 0.08385 something something. So my volume, I'm going to be running off the page here. I'm going to need to switch colors. The volume of carbon monoxide ends up to be, okay, so I'm getting a volume for carbon monoxide equal to 92.43 liters. And I think we can keep 3 sig figs. So 92.4 liters of carbon monoxide gas is produced when 96.25 grams of silicon dioxide reacts with carbon. That's it. That's how we would apply Dalton's law in this circumstance. First we have to use the pressure, the atmospheric pressure, and the water vapor pressure to figure out the pressure of just the carbon monoxide that we're in. So when you collect a gas over the water, then we want the pressure inside to be equal to the pressure outside, otherwise that line inside the tube of glass is moving. So this line right here is going to move until the force pressing down is equal to the force pushing up. In other words, what's pushing the water up in here is the air pushing down on the water in this tub, right? So if we have air pushing down on the water inside the beaker that's equal to the air pushing on the water outside the beaker, then that's when we know atmospheric pressure is equal to the pressure of the gases inside, the water plus the pressure of whatever gas you're interested in collecting. If the equalization does not occur, then the pressure difference has to be accounted for. So dinitrogen monoxide can be produced by the heat decomposition of ammonium nitrate. What volume of dinitrogen monoxide collected over water at a total pressure of 94 kilopascals and 22 degrees Celsius can be produced from 2.6 grams of ammonium nitrate, where we know the vapor pressure of water at 22 degrees Celsius is 21 torr. First of all, let's do with pressure. We have a total pressure, so our atmospheric pressure is 94 kilopascals. Where 101.3 is our standard pressure, then we know we're pretty close to standard pressure. 101.3 kPa is equal to 1 atmosphere, so we're going to use that and convert kPa to atmospheres. So in atmospheres, that is 0.9279 and a whole bunch more digits. Atmospheres of pressure for the total pressure. And the part of this pressure that is water at this particular temperature is 21 torr. So not a lot, but enough to make a difference. 1 atmosphere is equal to 760 torr, so that would be 0.02763 atmospheres. So the pressure of just our N2O gas is going to be the difference between those two. That would be 0.90031 atmospheres. All right, so we had 2.6 grams of ammonium nitrate, solid ammonium nitrate. Let's see, what else do we have? We know the pressure of the N2O gas that was collected was 0.90031 atmospheres. And the temperature was 22 degrees Celsius, so that's 295.15 kelvins. So first let's get to moles. We'll have something that we can actually work with then. For every 1 mole of ammonium nitrate, I'm going to have how many grams? Looks like I've got 80.05 grams for every mole. And now let's use the mole ratio from our balanced equation. For every 1 mole of ammonium nitrate, I'm going to get 1 mole of dinitrogen monoxide. And I just noticed in our balanced equation, it looks like we have a typing error. We should be dealing with this gas, not NO2. Otherwise, our equation doesn't really balance, does it? So I've got 0.0325 moles of the N2O gas at a pressure of 0.9 atmospheres and a temperature of 295. We need to find the volume of this. So that's nRT over P, 0.0325 moles. I'm going to keep my units in here so I know I'm doing it right. Times my gas, so 0.08206 liters times atmospheres over moles times kelvins. And then my temperature is 295.15 atmospheres. Divide by my pressure of just the gas I'm interested in, not the total gas of everything. Now we're going to double check that units actually cancel into something I'm interested in. Why did I put atmospheres there? That should be kelvins for temperature. Time for the calculator. The volume that I get is 0.8737 liters, and I get to keep only 2 sig figs. So we're going to call this 0.87 liters of dinitrogen monoxide. Now we have the mole fraction. Let me show you the mole fraction because this might make your math a little bit easier. The mole fraction is a dimensionless number that basically tells us the ratio of moles of a component of substance compared to the total moles in the mixture altogether. The symbol for mole fraction is called chi, which is like a goofy looking X, right? And it's spelled C-H-I, so you might call it chi, but its pronunciation is chi. And for any chi value, we're just looking at the part divided by the whole. So one component divided by all the components that there are. And it could be expressed as a mole ratio, but because of what we know, like moles of one thing divided by the moles total, but because of what we know about Dalton's law and how pressure is related to moles, then it could also be the pressure of our one thing divided by the total pressure of everything altogether. So however you can determine your chi value, it is going to be pretty useful to you. And there's an example in your pre-lab that deals exactly with the mole fraction. Let me give you an example here. The partial pressure of nitrogen in air is 592 torr. If air pressure is 752 torr, then what is the mole fraction of nitrogen? So to find chi for nitrogen, all we have to do is take the part that comes from nitrogen, 592 torr, and divide by the total pressure of all the air, 752 torr. And that's it. Now we have our mole fraction. And it's going to have, where torrs cancel, it's going to have no units. That's why it's called a dimensionless number. All right, I'm going to get to keep 3 sig figs here. But what we see is that we estimate nitrogen to be about 80% of Earth's atmosphere, where really it's 78.7% of Earth's atmosphere. Not too bad, huh? Pretty good estimate. That's how we find a mole fraction. That almost seemed too easy, didn't it? Let's try one that's a little more challenging. The partial pressure of nitrogen, if the container holding the air is compressed to 5.25 atmospheres. All right, so now we go from 700, whatever we have before, 752 torr, to now 5.25 atmospheres. Well, what do you want to do? You want to change torrs to atmospheres or atmospheres to torrs? Doesn't matter, but we can't compare one pressure, like the pressure of nitrogen, to the pressure of the total if they're not in the same units. So this isn't hard. We just have to do it one way or the other. So let's go ahead and change 5.25 atmospheres into torrs. Why? Because I like dividing by 1, that's why. 3990 torrs. So there's my total pressure. And the part that's coming from nitrogen is still 592 torrs. So 592 torrs divided by 3990 torrs. So now my mole fraction, chi, for nitrogen, is only 0.14837, and we're still keeping, what, 3 sig figs here it looks like? So 0.148, and I don't have any units there. So that's my mole fraction now that the container was compressed. That's all we do for partial pressure. Take the part that you're interested in this case nitrogen, and divide it by the total pressure of everything that there is. That's all. The part over the whole. Now we're done, I think. How about that? That's it for this podcast, and I will see you guys in class.